Large language models are probabilistic text generators. They compute the next token based on statistical likelihoods, meaning the same input can produce variable text strings. But enterprise software pipelines require the exact opposite: strict, deterministic data structures that produce the same result every single time to prevent application crashes. There is a common misconception that prompt engineering is just a matter of typing conversational sentences into a standard REST API. In a professional context, prompt engineering is the discipline of building precise software middleware designed to constrain and control these non-deterministic models. To bridge this gap, we must map the architectural journey from a raw natural language prompt to a multi-node enterprise pipeline. Managing the precise intersection between conversational interfaces and rigid software engineering is the only way to deploy production-grade AI safely. This diagram shows the base of our architecture, a single input node passing raw data into the central processing unit. We constrain this node using the 5 pillars: persona, task, context, format, and negative constraints. Without explicit boundaries, models often fail to extract data from messy, unstructured sources, frequently mixing the target information with irrelevant conversational filler. We use XML delimiters to segregate these variables. XML delimiters are tags, like bracket data bracket, used to wrap specific text strings so the model knows exactly where one piece of information ends and the next begins. We also implement null handling protocols. Null handling is a set of instructions that tells the model to return a specific null or NA value if the information is missing, rather than attempting to guess. To standardize the output, we use few-shot templates. A few-shot template is a prompt that includes several completed examples of the task to show the model the desired pattern. These examples demonstrate the required brevity, effectively stripping away the conversational fluff typically found in standard model responses. By enforcing these strict formatting boundaries, we establish the first layer of deterministic control over the output. Formatting handles the data's shape, but we also need to address logic failures and hallucinations, where the model generates facts that are not present in the source text. We implement chain-of-thought reasoning. This prompting technique forces the model to write out internal reasoning steps before providing a final answer. We instruct the model to evaluate multi-path hypotheses, checking different logical interpretations of a problem before converging on the soundest conclusion. This is followed by a self-reflection step, where the model compares its drafted reasoning against the negative constraints we set in the foundation layer. This cognitive pause prevents the system from generating data that looks syntactically correct but contains deep logical errors. Forcing this sequential scaffolding is the primary defense against catastrophic reasoning failures in a production environment. Even with sound logic, passing raw text into an application's codebase is dangerous. A single unexpected sentence can break the entire software integration. This rigid outer framework represents the system prompt. The system prompt is a set of high-level instructions, separate from the user input, that defines the model's core rules and operational boundaries. We use the system prompt to force JSON outputs. JSON, or JavaScript Object Notation, is a structured data format that software can parse automatically without human intervention. However, allowing user-facing inputs creates a risk where a user can try to override these instructions. This is a prompt injection attack, where a user inputs commands designed to hijack the model and ignore original system instructions. We build prompt injection defenses, creating a security perimeter that filters user input, ensuring it cannot override the engine's core system prompt. This defense ensures the JSON output remains structured and safe for the application to ingest. Secure JSON formatting combined with injection defense creates the necessary boundary for an enterprise-grade AI system. A single, massive prompt trying to perform 10 different tasks will eventually suffer from context dilution, leading to a drop in accuracy as the model misses instructions. Instead of one prompt, we build an automated pipeline that splits the workload into distinct parallel tracks. The router node analyzes the incoming request and determines its intent. The router then directs the data to a specialized subprompt, a small, highly focused instruction set optimized for that specific task. This compartmentalization ensures the model is never overwhelmed by conflicting instructions or irrelevant data. A distributed routing network maintains consistent output quality by ensuring each request is handled by a prompt optimized for its specific logic path. The final challenge is connecting this system to internal company data without exposing private information to the public internet. We use enterprise RAG, or Retrieval Augmented Generation. This is an architecture that allows the AI to look up facts from a secure internal vault, rather than relying on its internal memory. The data is stored in a vector database. This is a system that converts text into mathematical coordinates, so the AI can find information based on its semantic meaning. We prepare this data through chunking, breaking long documents into smaller, manageable snippets that the model can process easily. Metadata filtering allows the system to pinpoint exact records based on specific tags like dates or department IDs. We also apply role-based access control, or RBAC, to ensure the AI only retrieves documents that the specific user is authorized to see. This authorized data is then piped directly into our established JSON formatting nodes. This architecture grounds the AI in fact, preventing data leakage and eliminating the model's reliance on its own prone-to-hallucination internal memory. From a single input to a secure JSON output, we have mapped a complete architectural blueprint for deterministic AI. Chain-of-thought reasoning ensures the internal logic remains sound. XML and JSON protocols guarantee the data is formatted for software integration. Routing nodes manage the cognitive load to maintain accuracy at scale, and enterprise RAG provides a secure, factual foundation for proprietary data. Combining these nodes creates a system where AI outputs are no longer a matter of probability, but a matter of engineering. This architectural approach replaces simple natural language queries with a structured system of controls designed for high-stakes production environments.